In this screencast, we are going to talk about orbital hybridization as well as sigma and pi bonds. So when the 1s orbital of one hydrogen atom overlaps with the 1s orbital of another hydrogen atom, a sigma bond is formed. All single bonds are sigma, which is represented with the lowercase sigma, Greek letter, bonds. Okay, this bond is cylindrical, symmetrical, because the electrons forming the bond are distributed symmetrically about an imaginary line that connect these two nuclei. Okay, now let's look at, so we looked at hydrogen. Hydrogen is kind of our simplest molecule to look at. Let's look at something that's a step more complicated and kind of the bright shining star of organic chemistry, which is carbon, right? Well, when we look at carbon, we know that carbon has four valence electrons. And when we put these in a orbital diagram like this, they show up where there's two electrons at a lower level of energy, and then one electron in each p orbital at a higher level. Now, there's a problem with this. The problem is that in this depiction, carbon should only be able to form two bonds because it only has two unpaired electrons, right? So in this depiction, carbon should only be able to form two bonds because it has two unpaired electrons. Now, we know, though, from all of the molecules that we have isolated, that carbon forms, for example, with methane, forms four bonds. And so in the 1930s-ish, scientists had to redefine their hypothesis about orbitals because we know that carbon forms four bonds instead of two. We also know that these bonds are the same length, and the bond angles here are 109.5. Whereas if there were only two bonds here, those bond angles would be different. They'd be like 90 degrees. So instead, what scientists proposed is that we have a hybrid orbitals that have some S character and some P character. And so they believe, we believe, or propose that, right, we have these hybrid orbitals that are called Sp3, okay, that make up these bonds. And they have 25% S character and 75% P character from those orbitals, okay? So when we talk about this and we talk about hybridization, right, it's just the combination of two or more atomic orbitals to form the same number of hybrid orbitals, right? Each having the same shape and energy. So let's look at sp3 orbitals in more detail. When we mix the spherical 2s orbital with a dumbbell 2p orbital, we get this kind of 4 hybrid orbitals that have a distorted shape like this. So they're going to have a large lobe and a small lobe. And so this is what the Sp3 orbitals, we think they look like. And so you can see another kind of way of looking at it is we take the 2s orbital, we have the 3 2p orbitals, and then to form, right, when they hybridize, they would form a tetrahedron, right? Now, the bonds formed from hybrid orbitals are stronger than the bonds from pure p orbitals. Okay, and these 4 hybrid orbitals form 4 equivalent bonds. So each bond, when we look at methane, right, each bond in methane is formed by overlap of an Sp3 hybrid orbital of carbon with a 1s orbital of hydrogen. Okay, now all 4 carbon-hydrogen bonds are single bonds, so they're sigma bonds, right? Now, the other thing to notice here is when we look down here at ammonia, which is NH3, and oxygen, the nitrogen in NH3 and the oxygen in H2O are surrounded by 4 groups. So that makes them as well Sp3 hybridized, right? So 4 groups surrounding an atom will give you the Sp3 hybridization, whether those are bonds or lone pairs, okay? Now, maybe the burning question in your heart is, Dr. Pierce, great, 4 groups, Sp3 hybridized, but what if you only have 3 groups or 2 groups? And I'm so glad that you asked that. If there's a little skip there, I got real excited. So just, if it breaks up a little bit, just ignore that. So if you have only 2 groups or 3 groups, then you're going to have Sp2 and Sp hybridized. So when you have 2 groups, let's start here. Okay. You only have the S and the P here that are hybridized. So these have this Sp, it's got 50% S character and 50% P character. Right? And when you come down here where you have 3 groups, okay, you have 1 s orbital and 2 p orbitals, and those overlap to give sp2, and then you have 1 2p orbital that remains unhybridized. Okay. Now up here you have 2 2p orbitals that remain unhybridized. Now, these are the 3 common modes that we see in organic chemistry: sp3, sp2, and sp hybridized. To determine the hybridization, you need to count the groups. When you do that, right, count right? If there are 2 groups, it's sp hybridized. If it's 3 groups, sorry, let me just, that cut off part of it. It's sp2 hybridized. And if it's 4 groups, it's sp3 hybridized. Now, those groups, remember, are atoms and non-bonded electron pairs. So lone pairs, atoms and lone pairs. So let's do an example. let's say you have a question that says, what orbitals are used to form each bond in methane, right? Or methanol, which is CH3OH. The first step here is to determine the hybridization of each atom. Okay, so I'm going to look at carbon, and I'm going to say carbon here has 4 groups. So because it has 4 groups, it is Sp3 hybridized. Now, we have oxygen there, and we know that oxygen doesn't have a charge, and it's got 2 bonds. So that means it also has 2 lone pairs. And because of that, we say that also has 4 groups and is Sp3 hybridized. Now, all the carbon-hydrogen bonds when we talk about hydrogen, right, that's not in a hybrid orbital. It is just 1s, okay? So now, the second step here, step 2, is we need to determine the orbitals for each bond, right? So we need to determine the orbitals that make up each bond. And so all the carbon and hydrogen are going to be the same. And so here's how you do it. You come over here and you say, okay, hey, look, we have a carbon and it is Sp3 hybridized. And that's what you write down first. You say, great, carbon Sp3. You draw a dash, and then you look at the hydrogen, and you say, look, I know hydrogen's 1s. Hydrogen, 1s. Okay? That's all the carbon-hydrogen bonds. For the carbon-oxygen bond, you have to look at the hybridization of each. The carbon bond is still Sp3, and it's bonded to an oxygen that is also Sp3. So those are the orbitals that make up each bond. Then for the oxygen hydrogen, we say, look, that oxygen is Sp3, and we know the hydrogen is 1s. So you look at the hybridization of the 2 atoms that create the bond to determine the orbitals that are used to form each bond. Oh, no, I got really excited. Dang it. Now, when we talk about that hybridization, let's look at ethane. So we've looked at kind of methane. We're going to branch out and look at ethane. Based on ethane, each carbon atom is singly bonded to 4 other atoms, right? As a result, each carbon is going to be tetrahedral, and each carbon is Sp3 hybridized. And then all the bonds here are going to be sigma bonds. Okay. One of the things that's interesting is that if you take out your molecule kit and you build ethane, you are going to notice that rotation occurs around the central carbon-carbon sigma bond. Okay. So that's something that's unique to single bonds, right? We've got that rotation. Now, let's talk about double bonds for a second. We're going to look at ethylene for this, which is sometimes called ethene. And when we look and have a double bond, what's happening here is we have those hybrid orbitals with sp2, 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 and then we have a 2p, right, or a p orbital. So what happens is, for a double bond, you have one sigma bond, which is the overlap of 2 sp2 orbitals, right? And then you have one pi bond, which is from the overlap of the two p orbitals. Now we're going to visualize this on the next slide, but I want you to be aware that pi bonds are weaker and more easily broken than sigma bonds because the electron density in a pi bond is farther from the nuclei. Okay, so let's visualize this. When we look over here, okay, what we see is that we have our two p orbitals that are perpendicular to the sigma orbital here, and they come together and overlap to make the pi bond here and here. So the pi bond is going to be above and below the plane of the molecule, so it's sticking kind of way far out there. Now here's a big thing. Unlike the carbon-carbon bond in ethane, that single bond that will rotate, we do not see rotation in a double bond. So that rotation around the carbon-carbon double bond does not occur. Now, let's talk about triple bonds for a moment and the sp hybrid orbitals. When we talk about the sp hybrid orbitals and triple bonds, right, are made from, they have one sigma bond, right, from two sp orbitals that overlap, and they have two pi bonds from the p orbital overlap, because now we have two p orbitals here that are available to overlap. The sp hybrid orbitals are forming the, like for example, in this molecule, are forming the carbon-hydrogen bond here, and then the carbon-carbon bond here. And so we're going to have those p orbitals above and below the plane there. And we can see that here where they're, again, we've got one that is kind of perpendicular to the plane, and then the other one that's also kind of perpendicular to each other. And so we see that there's an overlap here and here, okay? And those form those two pi bonds that extend out from the axis of that linear molecule. So all triple bonds are composed of one sigma and two pi bonds. Here is a summary of what we've talked about. I find this to be, when I was a student, I found this to be incredibly helpful. If you have 4 groups that are bonded to a carbon, it's going to be sp3 hybridized. It's going to have a bond angle of 109.5, and there's going to be a sigma bond. And here in ethane, we would describe that sigma bond as a C sp3 C sp3 sigma bond between the carbons. If you have 3 groups bonded to a carbon, it's sp2. Those bond angles are 120. And the way we would describe this is one sigma bond and one pi bond. And the sigma bond is going to be the overlap of the hybrid orbitals, the sp2. And then the pi bond is the overlap of the p orbitals, the 2p here. Then for the number of groups bonded to carbon here, there's 2. It's sp, right? And you have an overlap of one sigma bond and 2 pi bonds. And that sigma bond is the sp, and the pi bonds are the p. Notice here that the sigma bonds are always made up of the hybrid orbitals. So let's do an example. This example says, determine the hybridization of the highlighted atoms of cyclohexanone. What orbitals are used to form the carbon-oxygen double bond? So we are going to come in here and we're going to look at the hybridization again. And to do this, we need to look at the groups. So when I look at this oxygen here, right, I know that we're going to have 2 lone pairs on this oxygen for it to be uncharged. So that means there are 3 groups on that oxygen. And so that's going to be sp2 hybridized. Okay. I'm going to look at this carbon next, and I can see that there's 1 group here, 1 group here, and 1 group here. And so because there are 3 groups on that carbon, that is also sp2 hybridized. Then I'm going to come over here and look at this carbon. Now this is really where you need to understand the structures of, like, the skeletal structure to a Lewis structure. I look at that carbon and I say, okay, hey, that's got no charge. So because that has no charge, I need to put in 2 hydrogens so that that carbon is bonded to 4 things, right? Because we know carbons are going to be bonded to 4 things. So because we have 4 groups there, we know then that that's an sp3 hybridization. So the next question is, what orbitals? Right? And so when we talk about what orbitals, when we look at the carbon double bonded to the oxygen, we know that that carbon is an sp2 orbital, and then the oxygen is also an sp2. But we need to know that there is going to be a sigma bond, and then because it's a double bond, there's also going to be a pi bond, and that pi bond is going to come from the 2p orbital of the carbon and the overlap with the 2p orbital of the oxygen. We'll practice this more in class. If you have any questions, please feel free to stop by my office.